Today I will going to discuss about the NaI practical, which is basically gamma ray spectroscopy. Now this is a this is a NaI TL scintillator detector. This whole process is called the gamma ray NaI TL scintillator detector. This whole part. Okay, now this portion is called the scintillator part, and this portion is called the PMT part. Do you know PMT means? PMT means a photo multiplier tube. Okay, now here we have NaI, but they are not compatible with these diodes, so that's why we used activated thallium. So that's and again it is called activator. Okay, now when my incident gamma ray comes this way, and basically we my excited element are situated here, and they emit gamma ray. Basically they emit all types of ray, gamma ray, beta ray, alpha ray, but here we will consider only the gamma ray. Okay, now this way gamma ray will come, and they excite the NaI, they excite the activator electrons. So they excite the activator electrons, and the electrons go to the excited state. Okay, electron go to the excited state. Now you know that gamma ray have greater wavelength, have maximum can be 5 mega electron volt. It can be 1 mega electron volt, etc. And the bond and the one electron comes out from a bond, it needs a 33 kilo electron volt. Okay, so it's a way more higher than so gamma ray has a higher way more higher energy than this binding energy. So electrons will go to the excited state, and it has some kinetic energy. But when electron go to excited state, it's try to comes out to a lower excited state or ground state. Okay, for doing this, so it emits some energy, which is the light photon energy, and electrons will go to the the ground state, and this photon will go towards this way, and here we have my photocathode. Okay, now first part, here you can see this optical contact, light guard, photocathode. Okay, this part is photocathode. Now what is optical contact? Optical contact is because we need other than the beta ray or gamma ray, it actually protects other from other rays. Okay, we only need gamma rays, we only detecting gamma rays. So when my this light photon this light photon comes here, it will create my photoelectron. Okay, this photoelectron go here, you can see my diodes. Okay, what is a diodes property? You know, diodes property is multiplying the electrons and energy coming to this way. You can see that here one electrons here, and it's multiplying this by 3, and again multiplying. That's the properties of the diodes, and diodes are actually connected with a high voltage source. Okay, so that's why it is actually a positive voltage source, and here we have photoelectrons, which is actually negative electron volts. So these negative electron volts are going towards these diodes, since it's a positive. So when my photoelectrons go towards this way, and they will multiply them, and here is my anode. Okay, now when these energies comes to here, and when this energy and this incident gamma ray energy and this energy will be equal, we will get one pulse. Okay, now this one I have said this is a photoelectric effect. Now here three types of effect are dominant, which first one is photoelectric effect, second one is Compton effect, third one is pair production. Okay, now let me write it. Photo, Compton, and it is pair. All right, now you know Compton effect. Now here and here we have lead guard. Okay, this is lead PB. Let me write it clearly. This is the lead guard, so that's why the radiations going through this cannot be comes out. And the Compton Compton effect occurs when the gamma ray will collide with the NaI activators, and it will recoil one electron and scatter a photon. Okay, a light energy photon. If the incident gamma ray has an energy is h nu, and so that I will get the h nu prime for scatter photon energy plus of t. It will recoil some energy, some electrons, and the electron has a kinetic energy. The kinetic energy is t. Okay. Now this photon will go towards this and make a and will make a peak. All right. Now comes to the backscattering process. Now when this incident radiation going some incident radiations going towards this way and collide with my lead guard, and they will here will again affect a Compton scattering type of effect. So and this will come to the scatter in this way. Okay, now this one is backscatter, and it will go towards this, and ultimately we will get here. Ultimately this effect comes to there here too. Now coming towards my pair production. What is actually pair production? For pair production we need a gamma ray which has to be energy greater than is equals to 1.02 mega electron volt. Why is that so? When my gamma energy comes here, and we will get a light photon, and this light photon can divide it into two parts. One is positron and one is electron, and those two have mass 0.511 each. Okay. So my light photon have to be energy of 1.02 mega electron volt. My light photon have to energy 0.2 mega electron volt. So when but after some time this positron and this electron will comes to a lower excited state by emitting some energy and recombine with electron. Okay, and this energy going to my final process, going for my final process. All right. Now here I'm going to discuss from here now. Here my anode have all types of pair production, Compton, and photoelectric effect of energy. So ultimately I will have here, and here I have a PRE amplifier which will amplify it, and this energy is actually equal to this energy. Okay, when these two energies will equal, then I will get a one pulse. So my next purpose is to discuss what I have here. Now here I have a PRE amplifier. Before discussing this, let me show you graphically. Okay. Now, if I have one excited cesium CS137. Okay. Now, if I have one excited cesium will emit some gamma ray, and my gamma ray will go to this direction, as I have said earlier. Now cesium has a graphical. Now if I have my baseline voltage this way and my count this way, I will get some graphical representation, something like this type of peak. This is my cesium 137 output characteristics. It is basically not exactly like this, but it's basically kind of like this. All right. So now how you will understand what is a pair production characteristics, how my pair production characteristics will be, and how my Compton characteristics is. Let me draw it. Okay, here I drawn XY plot. Now this will be my photoelectric, this will be my photoelectric, this will be my Compton, and here this will be my pair production. Alright, and if you have some kind of peak type of thing at Compton effect, it is for backscattering. Alright, now another question is important, that is to find the energy of an unknown sample. Now let us consider the two sample. One is cesium 137 and Na22. Here let us consider this one is unknown. Alright, and I have given energy of cesium of its peak value. Peak value means this position, have 662 kilo electron volt. Alright, and so I have to make this by my calibration curve, which is this part will be energy and this will be my baseline. So I will get the baseline of the peak value, and I have energy. So let us assume it is be here for cesium, and for calibration curve I know that the straight line will have to pass from its origin, which is let 0 0. So my calibration curve is this, it will be straight line, And so from sodium Na22 data, which is you have to take data, two sets of data. For one is for cesium and one is for sodium. You have two data for baseline, and one is count, and then you will have to plot this portion for one for cesium and one for sodium. Okay, you have to take data for sodium too. Now to find the energy of sodium, you have to take the peak value of sodium. Let us assume that let us draw let this is my sodium characteristics. Okay, this portion is count, and this portion is my baseline. All right, now this is peak, so you will have you can get the baseline here. Okay, this is baseline. So putting the baseline here, you can get the energy of unknown sample. All right. Now another thing is, some colleges may want you to do error-free calculation, error-free characteristics. Okay, so here what does mean that error-free? Now for error mean you have to calculate the background effect. For background effect, you have firstly before doing all these cesium data and sodium data or another sample data, you just have to take without sample. Okay, you don't have to give it here, put it here, and take the count, take the pulse like this. You can get baseline here, and and you can get count here. It's for background, and it is a kind of error. All right, and here what you have here you have for sodium and you for cesium. All right, and it is with background, and you just have to subtract this background part from this with this cesium data. Okay, so ultimately you will get here without background count. Okay, and then you have to you can plot it like this, and the same process will go on. Another question is, you have all discrete parts here. Here discrete parts, here discrete parts, and pair productions, Compton scattering, and these photoelectric effect, all are discrete part. But how you will get the linear one? How will get the linear energy? Because you can find the energy of sodium from this calibration curve, so that means you have linear energy. So for this discussion, let me go again here. Here what you can see, this is my high voltage divider pulse amplifier. Let me discuss high voltage source first. Now why high voltage source is used? High voltage source is basically used, most importantly used for diodes, that makes diode positive. So that's why photoelectrons are attracted towards the diodes. Okay, now going towards my these amplifier parts. Firstly, I have preamplifier. All right, is have preamplifier. Now preamplifier is a basic amplifier which will amplify the anode signal. It will amplify the anode signal. Now, yeah, I have already been discussed that anode signal, this signal and this gamma ray has the same energy. So here, this preamplifier will amplify this, and my important part is my linear amplifier, which is responsible to for linearity of my graphical characteristics representation. Graphical representation, this linear amplifier is responsible. After linear amplifier, this signal will go towards the screen, and from screen we can calculate the count or the graphical representations at CROs, etc. Now, one more important thing you have to know about CO sample. For CO, you will get CO characteristics. This side is count and this is baseline. You can get two peaks, two high peaks. All right. Why is that so? It is because, see, as I have fastly discussed that the gamma photon will gamma ray will excite the electron, and it will emit emit the lighter photons. Now, what happened at the case of CO? For CO, the de-excitations, CO de-excite in 2 times. It will de-excite in 2 times, in 2 states. All right, so that's why we will get 2 peaks. So it is very important to know. You have to know this. It is important for your exam purpose, for viva questions. Another important thing for your exam purpose, which is finding the resolution. How you can find the resolution? Now, going towards my curve, baseline count, baseline versus count curve. From here, I have my peak point. This, let us consider this. Now I have said this earlier. This is my cesium curve. Okay. Now I have peak point here. From peak point, I will draw a line from my baseline, on my baseline. Now on my base, from 0 to this, let us denote this C. All right, and from here to here, take the half of it, half of that line. So let us assume this will be here. So I have this width. Let us consider this width is del C. This little portions of baseline is let us call it DC, del C, and it is C. Now for resolution, you have R is equals to del C by C into 100%. Resolution is kind of sharpness, measuring of sharpness. All right. So this is important for your exam purpose, and you may get asked to write that resolution. All right. Okay guys, see you at my next video.